Welcome back. In today's lecture, we are going to learn how to decode time series data and master the mechanics of classic decomposition. When you look at a chart of stock prices, corporate earnings, or website traffic, you are actually looking at multiple independent signals tangled together into a single line. To extract meaningful insights, we have to isolate those signals. In this tutorial, we will take a systematic engineering approach to this problem. We will write Python code to build a synthetic dataset from scratch, blend custom mathematical patterns, and then use statistical decomposition to separate the trend, the seasonality, and the random noise. Let's open up the notebook and get started. First, we import Matplotlib library for visualization, NumPy to handle fast array calculations, and Pandas to give our data a structured timeline. We fetch the ACF function to calculate the autocorrelation from the Statsmodels library, and seasonal decompose to pick apart our data layers later on. First, we create our timeline. We are using the Pandas dateRange function to generate 100 consecutive timestamps. We start on January 1st, 2000, and set the frequency to month end, ME. This gives us a clean chronological index for our data. This is what the datetime index object looks like. Next, we create a sequence of numbers named T using NumPy linspace. This generates 100 evenly spaced values from 0 to 10. We will use this sequence as the independent variable to calculate our mathematical formulas. Next, we built the trend component. We multiply our time sequence T by 2. This creates a simple upward linear trend, simulating a steady growth over time. For seasonality, we'll use a sine wave. The 2π multiplier ensures a smooth regular rhythm over time. The multiplier of 5 drives the amplitude, controlling how high and low the pattern swings. This perfectly mimics real-world cycles, like predictable seasonal sales. Real data is never perfectly smooth, so we need to add some randomness. We use NumPy to generate noise from a normal distribution. We center it at 0 with a standard deviation of 1, creating a random fluctuations for each of our 100 data points. We add the trend, the seasonality, and the noise together. Combining these three distinct elements gives us a complex, realistic dataset. Now that our data is ready, we package it into a Pandas series. We pass in our combined data array and assign the time index we created earlier. Now every single data point is tied to a specific calendar month. Let's print the first 5 dates and the first 5 generated values in the console. Okay, perfect. Now let's visualize our combined dataset to see how these mathematical components look when they are blended together. First, look at the overall trajectory. The line clearly starts near 0 on the left and then climbs to a peak value of around 25 by the end of our timeline. The steady climb represents the underlying linear trend component. Second, notice the heavy rhythmic waves undulating across the entire chart. There are roughly 8 complete cycles visible across the years, showing the powerful influence of our sine wave seasonality. Lastly, the line is not perfectly smooth, it's jagged and erratic throughout. This represents our Gaussian noise, which simulates the real-world imperfection we expect to find in actual historical data. This chart gives us the perfect baseline before we attempt to separate these layers using classical decomposition. Let's use a quantitative tool to confirm the presence of our seasonal patterns. We will calculate the autocorrelation function, or ACF, using the Statsmodels library. We call the ACF function on our time series dataset, explicitly setting the number of lags to 20. This means we're going to look back across 20 intervals to see how past datasets correlate with the current ones. We then loop through these calculated values, print out a clearly formatted list showing each lag and its corresponding correlation coefficient rounded to 4 decimal places. At lag 0, the value is exactly 1. This is expected, as any data point always correlates perfectly with itself. As we move to lag 1, the correlation remains incredibly high at roughly 0.9. indicating a strong short-term dependency where yesterday's value tells us a lot about today's value. But watch what happens as lags increase. The correlation drops steadily, bottoming out around lag 5 at just 0.4. From there, it begins to climb back up, forming a distinct wave. It peaks at around lag 9 and 10, hitting values over 0.71 before starting to decline again. This cyclical rise and fall in the correlation coefficients is a textbook indicator of a strong seasonality. It confirms numerically what our eyes see in the plot. The data is repeating itself in a highly predictable wave-like pattern. With our autocorrelation analysis confirming a strong cyclical pattern, it is time to isolate the individual components of our time series. We use the seasonal decompose function from the Statsmodels library to do the heavy lifting. We pass in our time series data and specify two critical parameters. First, we set the model to additive because our components simply added together to form the final signal. And second, we set the period to 12, which matches the annual monthly frequency of our dataset. Once the decomposition runs, we extract the three isolated layers into separate variables: the trend component, the season component, and the residual component, which captures the leftover random noise. To verify the results, we print a quick snapshot of our first 10 rows of our newly calculated trend component. Looking at the printed result below, something immediately jumps out. The first 6 rows from January through June of year 2000 does not have any numbers at all. Instead, they show NaN, which stands for not a number. This is actually not a bug. It is a fundamental characteristic of how classical seasonal decomposition works. To isolate the trend, the algorithm applies a centered moving average. Because our period is 12, the algorithm needs a 6-month window of data both before and after any given point to calculate its moving average. Since there's no data points prior to January 2000, the first 6 months cannot be calculated, leaving them blank. The actual numbers finally kick in at row 7 on July 31st, 2000, starting at a value of roughly 1.33. From there, you can watch the trend climb steadily month by month, hitting 1.92 in August and 2.08 in September, and hovering around 2.0 by October. This gives us our first clean look at the true upward trajectory of our data, completely stripped of its seasonal waves and random noise. And finally, to wrap up our analysis, we want to see our hard work side by side. Instead of looking at individual snapshots or numbers, we are going to plot the original time series right next to its 3 freshly isolated components. We start by setting a large Matplotlib library figure with 4 rows and a single column. For the first subplot, AX1, we title it Original Data and plot our raw time series in black. In the second subplot, AX2, we plot our trend component in blue. For the third subplot, AX3, we isolate the pure seasonal component and display it in green. And finally, in the fourth subplot, AX4, we plot the residual noise component in red. We can see the mathematical magic of seasonal decomposition perfectly illustrated. The top plot shows our original messy data, which includes the trend, the seasonal waves, and the noise all together. But look at the plot below it, the second plot. This is our trend component. And even the edge effects from those NaN values we discussed earlier are resolved. What is left is a smooth, undulating line that reveals the true, steady, long-term upward trajectory of our dataset over the years. Next, the green plot isolates the seasonal component. It strips away both the upward trend and the random noise, revealing a perfectly symmetrical repeating sine wave. This gives us a flawless visual representation of the stable 12-month cycle embedded in our data. Finally, the red plot displays the residuals. This is the leftover noise once the trend and seasonality have been completely removed. It bounces around 0 with no discernible pattern or direction, confirming that our model successfully extracted all the meaningful structural information, leaving behind only pure random variation. With these 4 views stacked together, we have successfully reverse engineered our time series data from scratch. Thank you so much for watching, and I'll see you in the next lecture.